So, hello everyone. My name is Jean-Denis Duroux from the University of Toulouse in France. And I have the pleasure to chair this last session of today. 3 presentations are planned. Adrien Bartoli will give a long presentation, 45 minutes, and then 2 short presentations by Giuseppe Rodriguez and Francesco Colibazzi, 25 minutes each. A specificity of that session is that the first 2 presentations are about 3D reconstruction. The last one is about 3D printing. Another specificity is that Adrien Bartoli, the first speaker, is currently not available. You will therefore see the presentation in the form of a video, and of course, you will not be able to ask any question. Adrien is a professor in the University of Clermont-Ferrand in the middle of France. So let's start with the first presentation with this video. Thank you, Sylvia.
I'm Adrien Bartoli, and I'm presenting our work on seeing in 3D from a single image with geometric priors. If you see this video, it means I couldn't connect properly to the meeting, and I'm sorry for that. And you can of course email me any questions and comments. First, what is 3D reconstruction? So we could define it as the conversion or upgrade of one or multiple 2D images to a 3D model of the observed object or environment, which we'll call the structure. The idea is we film first with a camera, digital camera. We obtain digital images, and then we have an algorithm that obtain the 3D reconstruction, which is made of models for the camera, possibly, not always, and a model of the structure, which is either the object or the whole environment we're observing in the images. So the most primary representation of the structure is a point cloud, but this is quite a poor representation, so we have much more sophisticated ones. The first upgrade we can make is, of course, to have the topology, which is a connection between the points, and we can also have a texture map where we have the color of the points and sometimes in between the points as well, and properties like the differentiability, which allows us to access the derivatives of the surface that we're looking at, that we're reconstructing. There are 2 main approaches to reconstruction. The physics-based one is consists of analyzing and modeling explicitly the imaging process. So in terms of the geometry, which describes where the primitive from the world project in the image, and the photometry, which describes what's the color of the different pixels. And then in this approach, the recovery is based on using visual cues, which are cues from the image that tell us something about the 3D world. These visual cues are I mean, their use is handcrafted. So the first one is visual motion, which describes how things move across different images. And probably the other most famous one is shading, and then we have occlusions, blur, silhouette, and shadows, and there are others. This is the classical approach to 3D reconstruction. A more recent approach is the learning-based approach, where there is a reconstruction function which is learned from data, which maps the image content to the 3D model of the reconstruction. So in this approach, all the visual cues are not explicitly modeled, but they're rather combined implicitly into the reconstruction function. So this has advantages and disadvantages. In the physics-based approach, probably the most mature visual cue is the visual motion, and it led to the structure for motion and SLAM algorithms. And here I'm showing an example, a famous example of reconstruction of the Coliseum by structure for motion from many images. In this approach, there is the visual geometry, which describes the theory of what happens between multiple images geometrically. It's an advanced theory, and the fundamental assumption here is that the scene, the environment is rigid, so it doesn't deform across the different images. That's a very strong assumption. With these assumptions, we're able here to obtain reconstruction, which is quantitative. We can analyze the uncertainty, we can quantify the precision of it, and that's, I think, a very important feature of this approach. So now what happens if we relax the rigidity assumption? So we have still multiple images, but here we have an object which is not a building or a car or this sort of very rigid object. We have a soft or a deformable, generally speaking, object. So we don't have the same shape seen into the different images, even though it is the same object which is photographed. So in this case, rather than computing one 3D structure, we have to compute multiple 3D structures or 3D shapes, one per image. And here we're going to propose a physics-based approach to this problem, like in structure for motion. And we're going to use the visual motion across the different images to compute this reconstruction. So we're going to obtain a result which is quantitative and for which we can evaluate the uncertainty and the accuracy. So dropping rigidity means that we have to find other priors to constrain the shape for 3D reconstruction. And there are three main types of priors that we can use in this respect. There are priors on the shape. So here we're going to assume the shape is smooth, or at least piecewise smooth. And this is quite a widely applicable prior. Another famous priors on the shapes are low curvature and the fact that it belongs to a subspace, but we're not going to use them. The second type of priors are priors on the deformation of the shape, and we will use smoothness and isometry. So isometry means that the distances across the shapes are preserved between different points. That's very widely applicable priors as well. It means that the extension is limited. The other possible priors are low curvature, subspace, and small baseline, which typically happens when you process a video. And the last type of prior, which is probably the most important, is the fact that we can use a template, which is basically a known 3D shape in some reference configuration. So here, because we are observing a piece of paper, we know that at some point it can be made flat. And if we know the texture map of this object when it's flat, then we can bundle it together into a template. And this will be a very important prior. So if we have a template, then we have a very particular problem setting, which is called shape from template, and in which case we can solve reconstruction from a single input image and, of course, the template. I'm going to discuss this shape from template problem a lot in this presentation. The template can be a digital object model, like in this case the texture map of the paper, because we know the piece of paper can be a flat shape at some point, so this makes a perfect template. But for more complex objects, it can be computed using structure for motion or SLAM, or a 3D object scanner, or anything, or Kinect, anything that gives us 3D. But once the template is computed, it's fixed, and we can process any input images, any input single image of the object, and compute 3D reconstruction. So you have here an example of a more complex object, which is this juice bottle. The template is shown on the left, on the top left. So it was constructed with a 3D scanner, and you can show on the bottom video of shape from templates solved in real time, where someone handles and deforms this bottle in front of a webcam. In the middle you have the depth map, and on the right you have a textured rendering of the object. You can see that in spite of the occlusions by the hands of the person handling the object, the whole object is reconstructed. So this is because we have a template, so we can interpolate the depth of the object and the appearance of the objects, even though there are occlusions, and we can synthesize virtual views, as you can see on the right of the screen. So if we don't have a template, on the other hand, we have a different problem setting, which is called non-rigid structure for motion, which is a direct extension of structure for motion to the deformable case, and we can solve this with at least two images. I'm going to discuss this problem as well a bit more briefly than shape from templates. So this is my presentation layout. First, I'm going to discuss solutions we've brought to shape from templates, then the extensions of these two non-rigid structure for motion, so the case with template and the case without template. And then I'm going to show applications of these to a concrete problem, which is computer-aided laparoscopy in surgery. The approach that I'm going to follow is to try to reconstruct from only one point correspondence. Practically speaking, this is very important because it allows one to cope with correspondence errors and modeling error. So I'm going to explain this briefly with algebra, but there is a more complete story which we can find in the papers, of course, which involves Riemannian geometry and which makes the whole theory more sound. Then I'm going to explain this also for non-rigid structure for motion, and even more briefly with algebra than in the shape from template case. So let's start with shape from template. The first thing we have to do is modeling, of course. So imagine here that we have our template on the left, our input image on the right, and what we're looking for is the unknown 3D shape here on the top right, and we're going to assume it's differentiable as many times as we need. And in practice, we only need it to be differentiable around the point that we're going to reconstruct, of course. So we have a calibrated camera, so we have the projection function. We're going to reconstruct the shape in the coordinate frame of the camera. And here our template, we're going to assume it's flat, but this is without loss of generality. So this is a domain omega, which is a subset of R2. We're going to assume that we know the mapping from the template to the image, and that we search for the function that maps the template to the 3D shape. So let's pick a point P here in omega, small p, and the corresponding point, small q, in the input image. That's a correspondence, and this correspondence is given to us. Now what we are searching for is capital Q, which is a 3D point, so we are searching for x, y, z in 3D. So we want to find Q in R3 given the correspondence P to Q and the projection function pi. The first constraint we have is the classical reprojection that says that the 3D point Q we want to reconstruct projects on the observed 3D point small q, and this is written here as pi of capital Q equals small q. The second constraint we have is the deformation constraint, which is here the isometry. And you can think of it as a constraint that preserves the local neighborhood of the point. So if we take this green circle here in the template and we name it AQ, concretely AQ is a 2x2 matrix describing the shape of this circle, After embedding of the points and its neighborhoods to the 3D shape, we have that the structure of this circle here, which becomes AQ, should be preserved on the 3D shape. Concretely, we have written this constraint here, and mathematically it means that the metric tensor of the shape doesn't change between the template and between the reconstructed 3D shape. So with these constraints, these two constraints, we can wonder if we can already solve for the reconstruction. So let's count the unknowns. We have 9 unknowns, the position of the 3D points and the local structure around these 3D points of the surface. And then we have only 5 constraints, unfortunately. These are the reprojection and the preservation of the local structure. So of course, we cannot solve because this problem is locally under constraint. So we have to add new constraint to make it fully constrained. So the constraint we're going to add is the first order reprojection constraint that says that the local shape here on the 3D surface, a capital Q, projects on the local shape in the image, a small q, which is given to us as part of the point correspondence. Algebraically, this is expressed by this new constraint, that the derivative of the projection multiplied by the local structure matrix gives us the structure matrix in the image. This complete problem is called capital A here, and we can count again if we can find a compromise between the number of unknowns, an equilibrium between the number of unknowns and the number of constraints. So we still have 9 unknowns, which is good. And now we have 9 constraints, and this is important because we have as many unknowns as constraints, so there is hope that we may be able to solve this problem. So it's consistent, and the question is whether it's solvable or not. So for that, we need to understand the nature of the constraints in this system. The first one is linear, the second one is quadratic, and the third one is quadratic too for the perspective camera. So we have a system of quadratic algebraic equations, and if we compute the theoretical number of solutions, it's a lot, it's 128, but we've been able to show that it actually has a unique solution for the 3D points, and at most 2 solutions for the local surface structure around these 3D points, which is a good news. And we've been able to show as well that this system is equivalent to the pose from 3-point P3P problem if you take 3 infinitesimally close points. So this theorem is important because it helps us to understand several theoretical properties of P3P thanks to this new SFT problem. And importantly, we've been able to show that there's a simple analytic solution to this system, which we can compute extremely efficiently with some analytic procedure. Practically speaking, it's important because given 1 point correspondence, we can compute the 3D points and local shape structure, at least 2 solutions for it on the surface. The correspondences we consider are first order differential correspondences, and they're represented by a 2D affine transform, which models the local behavior of the transformation between the template and the image. And there are at least 3 ways to obtain this type of correspondences. The first way is to detect and match affine covariant key points. The second way is to use dense optic flow correspondences. And the third way is to fit a warp function to regular key point correspondences. So we typically use here the third way, which I'm going to describe. So here I'm showing the example of classical thin plate spline, which was estimated from SIFT key point correspondences established automatically. This warp is written eta, so this is a function from omega to r square, and it is represented here, visualized by this red grid, which is a regular grid in the template, to which we apply the warp to show how it behaves in the input image. So here you can see an example of reconstruction of deforming piece of paper. On the left, you can see the input video sequence, and we overlaid this white grid to show the behavior of the warp that we recovered. And on the right, you can see the texture maps reconstructed surface. What's important here is that so we use the template, this is shape from templates, and we processed every frame of the video independently, and you can see that still the result is quite stable. So another example that I'm showing is this balloon where you have the template here, the input video on the right, and the reconstruction on the left. Here, of course, we don't have isometry because there is extension on the surface, so we used a slightly different solution to SFT, which employed a conformal model, which is a model where the angles and not the distances on the surface are preserved. You can see, even though we've relaxed isometry, the result is still very stable. So there's a lot of extensions that we have looked at from this base framework. The first one, of course, is to use templates which are not flat, as in the case of the balloon or the piece of paper. Perhaps more as in the case of the juice bottle I've shown at the beginning. So it works similarly. The second thing was to try and compute the focal length of the camera. So in this case, we have a second order local solution. The solution I've shown is first order because we use the first order of the local motion derivatives. If we want to compute the focal length, we will need the second order derivatives of this. We have looked at conformal deformation. So this is the one I was explaining for the balloon example. So there is a first order local solution as well that gives the surface normal, not the absolute depth, but the surface normal. We have as well looked at equiareal deformation, which are the deformation that preserve the local area. In that case, we've shown that there is no local solution, at least we haven't found one. We have looked at other types of cameras, namely the affine cameras. So they are as well local solutions, similarly to the perspective camera. They are simpler than for the perspective camera. And we have looked as well as 1D structures. I've shown an example here where we try to reconstruct the shape of the road line here, shown in orange on this image here, from a template here, which we have constructed manually because the spacing between the different parts of this road line are standard, so we can form this template very simply. And here you can visualize the camera and the 3D structure we computed with the ground truth in black and the reconstruction in green, and you can see it fits quite well. Another question which we addressed is whether the warp is an arbitrary smooth 2D function. So basically, can you take any smooth 2D function and it will be an eligible warp describing the deformation between the template and the input image? And the answer is no. The warp function, at least when we have an isometric deformation of the template, is not an arbitrary 2D function. It has constraints because it's the perspective projection of an isometric deformation of the surface. And we've been able to show that it's characterized by a second order partial differential equation. So basically, if you define the warp as the composition of the embedding function phi and the projection function pi, we've been able to eliminate the unknown embedding function phi and to obtain this PDE denoted f in this equation, which is only constraining the warp independently of the 3D surface. So this concludes the part on shape from template, and we're now going to discuss the non-rigid structure for motion case. So the case where we don't have a template. First step is modeling. So we take 2 images at least, but the model is valid for more. And we assume that the intrinsics of the camera don't change. So we have the same projection function pi for all images. And we search for the embedding function, this one and that one, as well as the function that deforms the 3D shape from the first state for the first image to the second image. So the data we have to start off is a point correspondence Q1, Q2 from first to second image. And we're going to search for the 3D points corresponding to this correspondence. And the problem can be written, find capital Q1, Q2, given the correspondence small q1, q2, and the projection function pi. So the first constraint we have is the reprojection constraint, which just says that the 3D points project on the image points properly, as you can see into the system on the left. The second constraint is the deformation constraint, which is isometry. So for this constraint, we introduce these local surface patches here, as well as in the image. And in terms of the algebraic constraints, it gives, these are the followings, which simply represent the fact that the local structure of this surface patch doesn't change between the first and the second deformation, and as well that it projects at the right location in the image. So this is a system we call A0, which means it's the 0th order system that we build. And if we count the number of unknowns and number of constraints, we see that we have way more unknowns, 18, compared to the number of constraints. So we cannot solve this system. So we need to introduce more constraints. This is under constraint. So we are going to introduce the reprojection constraint at first order, which is importantly that this surface patch here will reproject at the right location in the input image. So similarly to SFT, where we assume that we had this differential correspondence of first order between the template and the image, here we assume that we have a differential correspondence between the first and the second image. So this adds this extra constraint here in the system, and this makes up a system that we call A1 because it's the first order system we built. So if we count the number of unknowns and constraints, we still have 18 unknowns, and we now have 15 constraints, so we have progressed. It's still not enough to be able to solve it. So the algebraic systems at 0th and first order are under constraint. We cannot solve them. But fortunately, the algebraic system at second order, A2, is consistent. I'm not deriving it explicitly because it becomes incredibly messy, because we have to introduce these second derivatives of the motion at the local points. This system can be reduced to 2 cubic equations in 2 variables, and it has between 2 and 18 solutions for the local shape structure, even though we cannot resolve for the 3D points directly. So concretely, it means we can't access the absolute depth, which is perfectly sensible, but we can compute the local normal of the shape at the correspondence. If we have a third image, then we can disambiguate and obtain only one solution for the 3 local shape structures, so for the 3 normals, even though we can never resolve for the 3D points. We have a conjecture that says that this system is equivalent to planar structure for motion for very close points, and we're working on proving this conjecture. In practice, the system can be solved numerically using the theory of resultants, and it boils down to solving a polynomial, a nonic, which is a polynomial of degree 8, which can be solved very efficiently with numerical methods. Here you can see results of non-rigid structure for motion with the isometric model. On an example of someone's bending one's hands, you can see the reconstruction in yellow and the ground truth in blue. So you can see the area is reasonable, it's below a centimeter. Here you can see another example where the reconstruction is in green and the ground truth in black, still with reasonable errors in the reconstruction. We've worked on several extensions of this theory, so we've tried, as in shape from template, to include the focal length of the camera in the end nodes, and importantly, we were able to solve for the focal length with the second order system. So we could add the focal length to the system and solve for it. We've been able as well to relax isometry to the conformal angle preserving deformation, so we can still solve from the second order constraints in this case. In terms of the equiareal deformation, so the ones that preserve the area, we haven't found a local solution. And we've also tried to simplify the solution to the affine cameras and found that we could also solve locally with a simpler solution than for the perspective camera. An important question in practice is the one of robustification, which means whether we can handle correspondence with errors. Like when you use SIFT on a pair of images, you always have correspondence error. So a robust algorithm should be able to do reconstruction and also discard the wrong correspondences. And here we've been able to achieve this by exploiting our very local solutions and embedding them into a pipeline that use robust statistics and the consistency checks of isometry across the different points. So we have these robust pipelines, which means that SFT and NRSFM can be used completely automatically on image sets. Lastly, before telling you about the application of this work, I want to quickly mention a recent result we obtained on using the learning-based approach for the SFT problem. So here we've used the template to simulate training data using Blender in many different imaging conditions, which means that we added blur, of course, a lot of deformations, lighting, etc., different camera parameters. And then we trained a network to do the reconstruction and registration problem for one specific template. So the disadvantage is that it only works from one template at a time, but the advantage is that it works extremely well. We used a few Kinect depth maps for the domain adaptation, so this is very light in practice to capture. And once the network is trained, it works extremely well, as you can see, for complex objects like the shoe and the dino, and a lot of different imaging conditions, deformation, occlusions, etc. So this is a very promising way, at least as a way to bootstrap the isometric physics-based approach, which I've described at length in the previous slides. So now I'm going to describe the application of these techniques to surgery, and in particular to laparoscopy, which is minimal invasive surgery in the abdominal or pelvic cavities. In this surgery, the surgeon holds a camera and tools which are entered into the patient cavity through lethal incisions, and they look at the inner anatomy on the screen. Here you can see a liver. In the real setting, it looks like this. So the camera, the laparoscope is here, and the two surgical tools are here and there. Of course, there are several persons around the patient who hold the multiple instruments and the camera. So in the classical laparoscopy, as it's done today, the surgeon takes a scan of the patient before surgery. Here you can see an example of a CT, and makes the diagnosis of whether the patient should undergo surgery from the CT, and then doesn't really access the CT during surgery. This is a problem in practice because when you have tumors inside the organ, even though you can see the organ very well, so you can see the liver here, if the tumors are endophytic, which means that they are inside the organ, you don't know where they are during surgery. And because you cannot touch, you cannot palpate the organ, it is really difficult to find where to cut to find the tumors. And of course, mentally aligning the CT scan to this laparoscopy image is extremely difficult, almost impossible to do. So the approach we're proposing is to fuse during surgery the preoperative CT scan with the intraoperative images to make augmented reality. So we've made a software for that, which is called Hepatology, that retrieves the video stream from the laparoscope in real time and fuses the image and displays this image to the surgeon. So this is a very difficult problem because we don't have fixed structures, and of course the organ deforms through the surgery. So our problem is the following. We have the 3D scan here, preoperative scan, the intraoperative image, and we want to make this fusion. So we start by simplifying the problem by segmenting the 3D scan. If we do that, then we access a surface model of the outer shape of the organ, but also of the inner structures. So you can see here we have a tumor and we have a vessel in blue that we segmented. And importantly, this problem is very similar to shape from templates. So if we replace the template by the model that we constructed from the CT scan here, and the input image by the input image from the laparoscope, then we can observe that the problem is to find the unknown 3D shape and the registration to the template. Because if we find the registration to the template, to this 3D model, then we can import the inner structures of the organ into the coordinate frame of the camera and then project them to the image to create the augmentation. So in other words, we're going to use the outer part of the surface to solve the registration problem, and then we're going to use this registration to import the inner structures of the organ from the pre-op scan to the image. So this is what it looks like in practice. We defined correspondences. Here we don't have point correspondences, but we have curve correspondences, even though the problem is really similar. And in this case, we've been able to import, so for this particular patient, the location of two small tumors, here in yellow, which were completely invisible, and part of the vascular structure. So what you could see deforming in this video is the registration going on between the preoperative model and this input image. So here you can see our system in action in the theater. The surgeon is here. There are two classical laparoscopy screens here, the ultrasound console here, and our system here. So here you have an initial augmentation, which you have seen already, that the surgeon used to resect these two small tumors. Then we did a second augmentation, in this case to verify that the tumors were properly resected. And on the right, you can see a post-operative verification that the tumor was indeed correctly resected, done by the pathologist. So this last video shows another system we have developed in action for the uterus, so not for the liver. Here you can see a small tumor in yellow, The white mesh is just the outer surface of the uterus. It's for visualization. Then you can see a big tumor as well in yellow here. And in black, this inner mesh here is the internal cavity of the uterus, which is very important to not harm during surgery for the future pregnancies of the patient. So with our system here, which works in real time, the surgeon is able to find the different inner structures and target specifically resection properly, and make the gesture more precise and surgery shorter. What's important is that the system works only at the beginning of surgery and stops when the incision starts, because then the organ deforms way too much, which is fine though, because when the system works at the beginning of surgery, the surgeon can mark the different locations on the surface of the organ for the different tumors, and this is a now well-established protocol, which works very well in practice. So again, I'm very sorry not to be here with you.
Thank you, Adrien. Thank you, Sylvia. It's a pity that Adrien is not reachable, but you can send him messages, of course. So now I give the floor directly to Giuseppe Rodriguez, and I remind you that you can post your questions in the chat, but you will have to ask the questions yourselves at the end of the presentation. Giuseppe?
Yes, I'm here.
It is your turn.
I start now?
Yes, yes, if you want, if you are ready.
Then I share the screen. I think it's this one. Can you see the slides?
Yes, perfectly.
Fine. So this is a joint work with Anna Concas and Caterina Fenu, who works in my university. And it is about the implementation of the photometric stereo with an unknown lighting solution problem, and an extension which is still on the way, but I will tell you what we are trying to do. Okay, the photometric stereo problem is a very basic, a very well-known problem in computer vision, but it has not been described yet in this conference, so a few slides are nice as an introduction. The situation is that there is an object and a camera, and their position are fixed. Some different pictures are taken from of the object with different lighting conditions. So there are different shades in the picture, and for this reason, it is one of the various possible shape from shading problems. This is a typical input to a photometric stereo problem for images, and once the problem is solved, one gets the object. In this case, the differentiable function. Our interest started during a collaboration with archaeologists who had the need to reproduce some rock engravings which were difficult to observe and were far from inhabited places. So they asked for a collaboration for trying to reconstruct them, and the choice fell on photometric stereo because of the easiness of data collection, in the sense that you just need a camera, a tripod, and a lamp light. The model is the well-known Lambert cosine law, and the law says that the intensity of the light reflected from a surface is proportional to the cosine of the angle between the normal to the surface and the light direction. It can be written in this way. So we have the normal in each point, the light direction, and the intensity. The rho is the so-called albedo. It is something which takes into account the kind of material, the painting on the surface, and so on. We will represent the solution as an explicit function. So there are some assumptions about the geometry of the problem, and in particular, we assume that the Q pictures are available. Q is the number of the pictures, so the different light direction with respect to the object. Each picture has a resolution R times S with P pixels, and it is vectorized. So each image is the pixels are in the lexicographic order. There are also some physical assumptions, and in general, none of these is perfectly met. In fact, the surface must be Lambertian, that is, it must satisfy the Lambert model, but this is not, I mean, this is an ideal situation. In particular, we will focus about the assumption that the lights are placed at infinite distance from the object. Also, the position of the camera is important, but it can be corrected by camera calibration processes. There are two main approaches for solving the problem. One is the so-called Hamilton-Jacobi formulation, where the Lambert's law is just written in terms of the solution. So one gets a system of first-order PDEs, which can be solved. There is a method. The method has been, the problem has been studied by Cosera from a rather mathematical point of view, and then under more applicative assumptions, many papers by Falcone, Maurizio Falcone. This is one of the first, I think, and Mecca. But we will use another approach, the so-called Poisson formulation, where the problem is broken into two sub-problems. The first one consists of determining the normal vector fields, that is, which is a discrete field because we have a normal in each pixel. And then, after differentiation the normal, we solve the Poisson equation, the standard Poisson equation. For both problems, the domain is a rectangle. We have Dirichlet boundary condition, homogeneous boundary conditions, and for the moment, the position of the lights are known. Well, one advantage of the Poisson approach with respect to the Hamilton-Jacobi problem approach is that the computation is decoupled into two simpler problems, and that it is possible to treat the problem of unknown lighting. That is, you can try to solve the problem without knowing where the light actually are. I don't know of any such solution for the Hamilton-Jacobi formulation. The drawback with respect to the Hamilton-Jacobi equations is that a larger number of images is needed. In fact, you need just 2 images with the Hamilton-Jacobi model, while you need at least 3 with the Poisson approach. But this is not a problem because at least in archaeological situations, one gets many images, more than 3 in any case, also because of noise to adopt a least square approach to smooth the errors. Another problem is that in the unknown lighting problem, you have to compute the singular value decomposition of a large dense matrix structure. In fact, this is the observation matrix, which contains all the pictures. I describe rapidly first the problem with known light position and then without. After discretizing everything on the grid of the pixel, we construct 4 matrices. R contains the albedo in each point of the grid. P is the number of pixels, so it is quite large, 10 power 6, 10 power 7. Q is the number of lights, and L is the matrix which contains the lights directions. N contains the normals in each pixel, and M is the data matrix. Each column is an image, so we have Q images. P is order 10 power 6, 10 power 7, or even more. Q is order 10 in general. after rewriting cleverly the computation, one gets this matrix equations, which links the three matrices R, N, L to the data matrix M. If the light's position is known, then you know L, and it is easy to obtain the matrix N tilde by multiplying M times the pseudo-inverse of L. This also shows that as L has 3 rows, to compute a unique solution, you need at least 3 columns, that is 3 lights, so 3 images. If you have more, it is good because you can solve the problem in the least square sense. And so we use the pseudo-inverse here rather than the inverse. After computing N tilde, it is easy to separate the albedo matrix from the normal vectors matrix. Okay, in the end, one solves the Poisson equation. Now, one of the drawbacks of this approach, at least in practical application, is that one has to know the light's position. But, well, it would be better to be able to take the picture without too much attention to where the flash lamp is actually placed. And luckily, Hayakawa in 1994 solved the problem, showing that if at least 6 images are available, then the light's position can be estimated directly from the data. Obviously, still in ideal condition, that is a Lambertian surface and lights at infinite distance from the object. I give a sketch of the construction because it is useful to understand how it works. It starts with computing the SVD of the data matrix. This is the heavy step. And this allows to create a rank 3 tentative factorization of M. This is still not an acceptable factorization, and it has to be corrected. It is a well, this is good. It is the best rank 3 approximation to the data matrix, but it's not compatible with the problem. To do this, this is the Theorem Probe proved by Hayakawa. You need to impose that the column of B are of unitary length, so the normal are unitary vectors. To find such a matrix B, which normalizes all these vectors, one can write the problem in this way, where G is a positive definite matrix, and after a few passages, one finds that he has to solve a linear system where the matrix H has 6 columns and Q rows, where Q is the number of lights. So the condition that if at least Q lights are available, then the matrix is square or overdeterminate, and the least square solution admits just one solution. Otherwise, there is not a unique solution. Well, even if Q is 6 or more, this doesn't mean that the matrix has full rank, but this is a condition which is easy to obtain. After obtaining G, one can obtain B, which is needed to correct the factorization by a Cholesky factorization. An important thing to notice is that only the relative position of the lights is determined. In fact, if we have an admissible rank 3 factorization, for example, the one coming from the Hayakawa formulation, then any orthogonal matrix multiplied times the 2 factors produces another admissible factorization. This means that we don't know the right orientation of the surface. The surface can be rotated, and there is no way for knowing the right rotation. Well, to tell the truth, there is not such a right rotation, because once you have the surface, whichever the orientation, it is the surface as well. But if you want to express it with an explicit function, well, the surface has to be to have just one value for each point of the domain. So it has to be almost horizontal, let's say. Okay, but this finding such a suitable orientation, it's easy. There are various possibilities to do this. Well, if you add some more information about how the pictures are taken, in fact, in a famous paper, it was proved that there is no way to get the right orientation directly only from the data. You need some more information, but in general, it is not difficult to add such information and obtain a reasonable rotation for the surface. Here is an example. These are 7 digital pixel synthetic picture of the surface you saw before. These are the light direction which produces those pictures. The pictures were digitally generated with the lights at these directions. This is the singular values of the data matrix, showing that the rank is numerically 3, as it should be. There is a big gap between the sigma 3 and sigma 4, the fourth singular value. And this is the lights coming out from the Hayakawa procedure. They are rotated with respect to the original one. And if you take a look, there is also an axis inversion, so a space inversion. In fact, the original picture turn in counterclockwise way, while these are turning in the opposite direction. Anyway, as I told you, adding some more information, it is possible to find a right rotation and a space inversion for the lights, and the error is very small. So working with digital images, we get just a very small error on the position of the lights. Okay, the reconstruction error is not so small, but just because here the pixels are just too few. I mean, we have a grid of 100 times 100 pixels, so it is not enough to have a good finite difference approximation of the surface. This is a real-world data set. This shell has been, the picture were taken using sunlight, so the sun is at infinite distance, at least approximately. The rank 3 condition is not so well verified. There is a gap between sigma 3 and sigma 4, but not as large as with digital data, with synthetic data. These are the directions of the lights reconstructed by the Hayakawa procedure. And this is the shell. Well, the shell is not so bad, as you can see. Well, I'm not able to move it. Maybe this is a problem with Zoom. Okay, but okay, this is the two different view of the reconstruction. Now, the next problem is what happened if the lighting conditions are not ideal. That is, if the light is not at infinite distance, so that the rays are parallel, but if it is a finite distance, so the rays are incident. Well, what happens to the reconstruction? This is another data set. This was taken from a piece exposed at the Museo Egizio in Torino. It's a Ptolemaic stela, rather large. I will show you a picture later to see how large it is. In this case, 8 pictures were taken, and the lights were quite close to the surface. As you can see, the rank 3 condition is not verified at all. This is the reconstruction, and I mean, the engravings are are reproduced quite well, but there is I mean, the surface, which was originally flat, is curved, and this curvature is due to the fact that we are solving a problem with the lights close to the object with a model which assumes that the lights are at infinite distance. I have the model here, but maybe I don't know if I'm able to move it. Yes. And you can see that it is quite curved. Also changing the lighting, you can see that the engravings are quite well reproduced. Okay, so this is a synthetic data test to understand what happens. And if we generate digital images with lights at infinite distance and then at a shorter distance from the object, these are the errors in the light's localization and in the surface reconstruction. So the errors become quite big as the light gets close to the object. On the contrary, if we are able to process a small portion of the object, then the surface is almost flat and we get reasonable reconstructions. This is not strange. In fact, I mean, the idea was, well, if a small portion gives a good result, we can decompose the domain in many subdomains, so a domain decomposition approach, and process each domain on its own. The motivation is that if rays are divergent for the whole domain, if the light is placed close to the object, then for a small domain, the rays will be almost parallel and we will have a reduction in the error. This domain decomposition approach may be useful at various levels. In fact, one possibility, and this is what is generally done with domain decomposition method, is that you can parallelize the algorithm and so optimize performance. So we will have to solve smaller problems, and the SVD we will have to compute, which will be of smaller data matrices. And we will be able also to use parallel architectures to solve the problem faster. The other advantage is to reduce the distortion, as I told you before, because the light is far for a small subdomain. Other possible application is to implement a standard Schwartz domain decomposition method for solving the final PDEs. This could also be done. And also to use the information about the location of lights in each subdomain to understand where the lights actually are with respect to the object. Knowing this position could allow to use a more complex model which does not assume lights at infinity to reconstruct the surface. For the moment, we are focusing just on the first two aspects of the problem. Which is the main difficulty in doing this? Let's just assume that the domain is subdivided in a 3x3 grid of subdomains. Then, if you apply the Hayakawa procedure to each of these domains, in each domain, we will have a different orientation of the system composed by the lights and the normals. And I mean, we don't have a way to put all this domain in accordance. That is to find a different rotation for each domain, which takes the system in the same situation. And we have to synchronize all the solution to get the normals in the right position to solve the final differential problem. Well, if lights are at infinity, then the lights will be seen in the same position from all the subdomains as they are very far. And so we will be able to use the system of the light direction as a reference to find a common rotation for all the subdomains. But if lights are at a finite distance, this is not possible because lights are seen from a different point of view from each domain. So something different has to be done. The approach we are trying to use is this one. We consider a small overlap between the domains, and the dots represent the normals, so the pixel in each part of the domain, and the red dots represent the normals which belong to two closed domains. The idea was to solve the problem in the first domain, find the normals, find any acceptable rotation which takes the surface in more or less horizontal position, and then use the normals on the north boundary of this subdomain as a reference for the solution in the next subdomain. So after solving the problem in this domain, we take the normals in the south border in the same position of their normal in the north border of the previous domain. And then I will tell you how to do that, but anyway, this is the trick. Then we pass the next upper domain, passing the normals again on the north boundary. And this step has to be done sequentially. At this point, we pass to the subdomains on the right, the normals on the east boundary to construct the next three subdomains. And this computation in principle can be done in parallel. And then another step to obtain the other three subdomain. All the normals can then be assembled in a single discrete vector field. And the next step is to solve the Poisson equation on the whole domain. Now, how to find the right rotation for the normals? Let's call N1 the north normal of the first domain and N2 the south normals of the second domain. We need a unitary matrix Q, a 3 by 3, because here the dimension is 3, so that Qn2 is equal to N1, or better, with a least square approach, then some kind of a norm of 2 norm is minimized. In this case, we are using the Frobenius norm, because for the Frobenius norm, there is, the solution of this problem exists. It consists in computing the SVD of the product N2 and 1 transpose, and then Q is just V times U transpose. This is a classic result, I think, from the 50s, but there is a nice review by Nick Hayam in a book chapter where all these matrix approximation problems are listed. This is another SVD which has to be solved in each subdomain, but this matrix to be factorized is 3 by 3, so it doesn't really take time. Which is the situation now? We have a MATLAB suite for the PS3D solution with unknown lighting, which is quite well working. And we are working to the new version for the domain decomposition approach with this trick of the normals, but we are still far from having a final version. We are still optimizing it. We run this software on syntactic dataset quite small, so still not, 1 megapixel pictures. And we observed a significant reduction in the reconstruction error using larger grids. At the moment, we are not able to use very large data sets, so we cannot take a largest domain decomposition, but this will be done in the future. And this is the end, and this is the original stele. And to show you how large it is, I pictured it with my daughter Laura a few years ago. So thank you for your attention. I finished.
Thank you, Giuseppe. Thank you for this nice contribution and the original idea to subdivide the domain. There is no question in the chat, but probably some people have questions, as I know that, for instance, Yvan Keo has one question, and Michael after Yvan. Yvan, can you activate your microphone?
Yeah, can you hear me now?
Yes.
Yes.
Yes, Paul. Thank you very much for your talk. It was very interesting. I have one question on the domain decomposition approach that you proposed. Is how can you ensure that at some point you do not encounter a planar patch? In which case the matrix should not have rank 3, I think. And what happens if
Sorry, what planar?
So when you decompose your domain into small patches,
yes,
it might happen that you look at a image patch where the surface is a plane.
Yes. No, obviously.
And so what do you do then?
In case it is well, it is a plane. Should it be a problem? I mean, in this case, the normal will all be vertical. I have just to find the right rotation. No, I don't think it is a problem. I think we applied it to some problems in which the part of the image is a plane. At least when the object is placed on a plane background.
Okay.
But okay, I have to think about that. I never thought it was a problem, but I will construct some example just to see what happens. Thank you.
Okay, yeah, I think it will be interesting. And also, I had another related questions. Is so from what I understand, so you solve on one patch and takes this solution to solve for the next patch. And wouldn't it make sense to solve globally for all patches together, like to avoid bias accumulation, for instance?
Well, the problem is that we can solve even all the problems together, because solving on each subdomain, you find the normals and the lights. But you need to find then a rotation so that all the normals are, oriented in the same way somehow.
Mm-hmm.
Because of the bas relief ambiguity, you actually don't know which rotation is applied in the factorization. You remember in this wait. Okay, the problem is this. From the factorization of the data matrix, I get two matrices. And here between the two, there may be a Q transpose Q.
Yeah.
So you have to find the same Q in somehow for all the domains. But the problem is that all the domains need a different Q, because you start with a tentative rank 3 factorization, which has no geometrical properties. So for the moment, the only approach I was able to find is to use a border of each subdomain to find the right rotation for the closed domain. Obviously, other approaches are possible, but for the moment, this was the only one which gave some results.
Okay, I see. Yeah, makes sense. Thank you very much for your answers.
Thank you.
Thank you, Ivan. Michael?
Yes, hello. Hello, Giuseppe. Thanks for the nice talk. Some part of my question was already answered. I have another one, because at the beginning I was slightly distracted here in home office. So is your camera model perspective or orthographic?
No, theoretically it's orthographic. And in fact, even in the ideal experiment with a shell, I have the original shell. There is some curvature in the shell, which is probably due to the fact that the camera was too close. So there must, some kind of a camera calibration approach should be applied.
I also had, it's, of course, also in the applied photography in the museum, also the camera was quite close to the object. So intuitively, I would also think that the deformation that you observe is probably more due to lighting, but it could also be due to perspective distortion.
I think it is. Both effects are producing the curvature, but from these results, I was quite confident that. I think that correcting the light with the subdomains should give better results. Then finally correcting the perspective would give an accurate reconstruction. But for the moment, we are concentrated just on the lights.
Okay, thanks.
Thank you.
Okay, thank you, Michael. Is there any other question? If not,